Hi. Hello everyone. My name is Keishiro Uragaki. In this presentation, I'd like to tell you two things. At first, please don't catch a cold before the presentation. Second, your witness perception can be easily manipulated with image projection. We will show the proposition through a sound-used interface at this presentation. Here you can see the movie of our interface. This is Fluidized Bed Interface, which is a haptic technology capable of presenting instantly the tactile sensation of solid and liquid, like this. This phenomenon is widely known in the industrial field, and the mechanism is very simple. The sand in the tank behaves like liquid by only sending the air uniformly from the bottom. Sand is constantly agitated by the air. You always feel sand is rubbed on the hand. However, this sense of resistance feels like liquid because the bulk-specific gravity of the sand is close to that of water. The fluidized bed interface has the advantage of haptics of sand and liquid. However, the change and the tactile sensation from sand to liquid is visually unclear because the sand surface is sandy. It is known the appearance influences the tactile impression. The agreement between the appearance and tactile sensation of the user interface is important from the usability. In order to improve the visual liquidness of the interface, we derived a solution with a spatial augmented reality-based method called sand to water. Our method is designed on the basis not only mere fluid simulation, but also visual liquidness perception. We will show the validity of our method by qualitative evaluation through user analysis. Sorry. Our method makes two contributions. We developed the method to improve the visual liquidness impression of the fluidized bed interface, which can be available for various applications. For example, it will be used as a stage devices by switching fluidization. This is the other example of the stage device. If you touch the surface of our system, many doors appear from underground, like this. In addition, the interface can be used in the amusement park as a surfing game. It may be a little dangerous. Furthermore, we evaluated the visual and tactile liquidness qualitatively. The fact is useful for the study human texture perception field, which has been actively studied in recent years. As a method to improve the visual liquidness impression, when a user touches the sand inside the fluidized bed interface, we introduce a projector camera system, a user touch detection method, and visual effects. This system configuration is shown on the left figure, and the actual system on the right figure. We structured a projector camera system embedded in the fluidized bed interface. For the calibration of the depth camera and projector, we introduced 4 markers with retroreflective materials affixed to the corner of the tank. Using this system, we projected a liquid-like image on the surface and fluidized bed interface. The tank of the interface is filled with sand, so therefore we introduce a touch detection method with a depth image. First, a depth image in a state where no interaction is performed is acquired as a background image. Next, we take the distance from the background and depth image obtained for each frame and evaluate the difference image for each closed region. Thereafter, if the distance of the centric position of each region is equal to or smaller than the threshold value, the region is regarded as a touch region. In this research, we assume the visual recognition impression is composed of three elements: wetness, smoothness, and transparency. Sayama showed we perceive the wetness impression of object surfaces using color information through psychophysical experiments. If the saturation and luminance of the surface are improved, the wetness impression will be also improved. Koike reported there is a negative correlation between the liquidness impression and the average discrete operation of the optical flow in images observed by us. That is, if the image observed by human is moving smoothly, the visual liquidness impression increases. In addition, Koike examined how the distortion of the liquid bottom causes the liquidness perception. We can perceive the existence of a transparent liquid only from the dynamic deformation from the liquid bottom texture. Following these researches, we consider wetness, smoothness, and transparency to be critical factor for visual liquidness perception. The projected image, which improves the visual liquidness impression, has a layer structure, and rendering is performed by parallel projection after generating images in each layer. The image generated with our method is composed of three layers. Ground layers as wetness to the texture of the ground. Liquid bottom layer distorts the image like liquid to as smoothness and transparency. A liquid surface layer simulates 2D fluid flow and reflects the movement of object on the liquid surface to as smoothness. The method is developed based on the three factors of visual liquidness perception. Sion proposed an image transformation method that manipulates the wetness perception. The method consists of two steps, which are skewing the luminous histogram in the image positively and improving saturation of the full image. This transformation is very simple, but developed based on the fact we perceive the wetness using color information. We adapt this transformation to the bottom texture at the ground layer. Koike reported we can perceive transparent liquid with dynamic deformation of the bottom texture. Following the report, we introduced a simple method to distort the texture by multiple circular sine waves at liquid bottom layer. For improving smoothness, we add ripples based on the 2D wave equation defined as the top equation to the layer. Next, we introduce a 2D fluid simulation based on the uncomposed Navier-Stokes equation expressed in the bottom equation at the liquid surface layer. We impart smoothness to image by moving bubbles, which are phenomena peculiar to liquid, according to the velocity field obtained by 2D fluid simulation. Additionally, bubble disappearance points were used as ripple generation points. Also, our visual effects don't reproduce the actual movement of liquid, but our method is demonstrated as a sufficient technique to impart visual liquidness to the Fluidized Bed Interface. We conducted user analysis in order to check the correspondence between the appearance and tactile sensation and verify whether our method could make the interface more visually liquid. We also evaluated qualitatively the definition of liquidness. Subjects evaluated the tactile sensation and the appearance of the interface and responded with their subjective impressions in a 7-level assessment based on the semantic differential technique. These experiments were done under 4 conditions called non-OF, OP, and both. For example, none is a condition not projecting the image or the surface and not fluidizing it. That is, it's only sound. We asked them to put their wrist inside the tank, and move without any accessories on their hands for about 3 minutes for each condition. First, we clarify that a change of the appearance of the interface while fluidizing is unclear, and validate our methods through correspondence between the tactile sensation and the appearance. When only fluidizing, the deviation could be shown significantly. In other words, there is a divergence between the appearance and the tactile sensation. After all, the change of the appearance is unclear. When projecting the image with fluidizing, the deviation could not be shown. This result indicated our method could correspond between the appearance and the tactile sensation. In order to show whether it improves haptic liquidness of the interface, we conducted the honestly significant difference test of SIGCHI for haptic liquidness for each condition. When fluidizing, image projection could not influence haptic liquidness. However, when not fluidizing it, the difference whether projecting the image or not is shown significantly. This result implies image projection has potential to add haptic liquidness to the fluidized bed interface. As a previous analysis, we conducted the test for visual liquidness for each condition. The appearance of the fluidized bed interface is more visually liquid through the image projection when both fluidizing and not fluidizing. These results verify the image projection. In addition, the fluidization itself might have the ability to enhance the visual liquidness. We show the variables related to liquidness because the definition of the liquidness is not revealed in the previous box. We enumerate items correlated with haptic or visual liquidness through qualitative evaluation. Haptic liquidness is related to the smoothness, the difficulty of the rotating the hands, the stiffness, the wetness, the buoyancy, and the friction. Visual liquidness is related to the smoothness, wetness, and transparency. These results may contain spurious correlations, but intuitively valid, and correspond to the hypothesis that the visual liquidness is related to these 3 factors. So our method is valid to add visual liquidness to the fluidized bed interface. Our method, called sand water, is a solution to the problem that there is a gap between visuals and haptics of the fluidized bed interface when fluidizing. And the projected image enhances the visual liquidness of the interface. We also found the fluidizing of the interface can enhance the visual liquidness of the projected image. The fluidized bed interface extended with our method is useful for stage devices and amusement parks as a novel presentation, and the analysis of the mechanism of human liquidness perception. This movie is taken at DC Expo, which is an exhibition event of promotion technology. Many people touch our system, and some children play it for an hour at the most. Our system is very enjoyable, but it has a disadvantage. When tidying up, the venue will be covered with sand. Therefore, it is necessary to make the room sparkle. This is my conclusion. Thank you for attention.
I'm wondering when the surfing game will come to our local arcades. Any questions about this exciting work? Okay, so I'll maybe ask this. So you have how many pumps inside the box? Are you using a single pump to create the sensation of smoothness? Is this like one big pump? So my question is, can you create local differences inside the box? So you can have maybe one area which is a bit stiffer, another area where it's smoother, to create these kind of different viscosity levels. Is that possible?
Yes.
Have you tried it? That would be interesting. Like you could, oh yeah, okay. Yes, I missed that. But so how fine grain is that? How can you? Is it like really half of the box, or can you create very local areas? Like like in the four corners, can they have different levels of stiffness?
Do you mean so the scale of the change of haptic area? なんだろう。Sorry.
So I mean, I guess it depends on where you put the pumps, right? I mean, if you can cover maybe the surrounding areas. So let's say if you have like a sand pit, you probably will have difficulties targeting the center, I guess. But you can maybe be a little bit more flexible around the borders. I mean, we can see it on the animation here.
Sorry.
Any questions? No. Okay. So maybe thank our speaker again. Thank you.